Integration of rational functions by partial fractions. First, let's talk about what it means to be a partial fraction decomposition. So we know from algebra that if we add or subtract fractions together, we have to have a common denominator. So for example, 2 over x minus 1 minus 1 over x plus 2 can be combined into x plus 5 over x squared plus x minus 2. And all we're doing here is multiplying the numerator and the denominator of each fraction by the factor needed to get a common denominator. So this is what you might call combining fractions or adding fractions. A partial fraction decomposition is when you do the reverse. So for example, with this fraction right here, x plus 5 over x squared plus x minus 2, we can decompose this first by factoring the denominator, which we know is going to factor into x minus 1 times x plus 2. And then because your original fraction is a proper fraction, which we'll talk a little bit more about in a minute, but basically the degree of the numerator here is less than the degree of the denominator. Since that is true, we know that when we break this down into the sum of two fractions that have each of those factors in the denominator, we know that the numerators here must be constants because each of these must be a proper fraction as well. So in other words, if this is a first degree polynomial here, we know the numerator has to be a constant, which I'm just going to call a. And same thing in the second fraction. The degree here is 1, so the numerator has to be a constant. And so the method of partial fraction decomposition now involves solving for a and b so that we can take the original fraction here and break it apart or decompose it into smaller fractions, the sum of smaller fractions. Now, in this case, we know that a is going to end up being 2, and we know that b is going to be negative 1, because again, this fraction came from subtracting these two in the beginning. So to make a long story short, a partial fraction decomposition is when you take a rational function and you pull it apart into its basic fraction makeup. So let's talk briefly about proper rational functions and improper rational functions. So a rational function is a function p of x divided by q of x, where p of x and q of x are both polynomials, and we say that it's proper if the degree of the numerator is strictly less than the degree of the denominator. And we call it improper if the degree of the numerator is greater than or equal to the degree of the denominator. And if it is improper, you can do long division to break it up in this format, where you have some polynomial s of x plus a remainder polynomial divided by the divisor polynomial. And we'll talk more about how to do this. When doing partial fraction decompositions, you can only perform that on proper rational functions. So if your rational function is improper, you must use long division before trying to break it down into partial fractions. Now, the whole point of doing this is to be able to integrate functions, find antiderivatives of functions. So let's take a look at this example. Here we have the integral of the rational function x cubed plus x over x minus 1. I want you to notice that this is an improper rational function because the degree of the numerator is 3 and the degree of the denominator is 1, and 3 is bigger than 1. So what that means is that we need to do a long division problem first before attempting to do anything else. So let's review long division. We have the denominator x minus 1 is being divided into the numerator x cubed plus x. And remember, when you do long division, you want to leave a space for any missing powers of x. So for example, here we have 0x squared, and then we also have 0 on the end. Now, I don't want to teach long division here, but I will briefly go through the process. We're going to say that x goes into x squared, x goes into x cubed, x squared times. And then we have to multiply x squared times x, which gives us x cubed. And then x squared times negative 1 gives us negative x squared. And you can see exactly why we put the 0x squared there. It's so that if we get an x squared in the multiplication process, we have somewhere to write it. Now, the most important part of a long division problem, remember, is that after you multiply, you have to subtract these, which really just means you need to change the sign of each term. Now, x cubed minus x cubed is 0. 0x squared plus 1x squared is x squared, and then the plus x comes down. And now we repeat the process. X divides into x squared, positive x times. X times x is x squared. And x times negative 1 is negative x. And then remember, you have to change the signs once again. Combining like terms, we get 2x. And now x goes into 2x positive 2 times. And 2 times x is 2x. And 2 times negative 1 is negative 2. And once again, change the signs. And the remainder is 2. And so now we can write the original fraction, x cubed plus x over x minus 1, is the same as x squared plus x plus 2 plus the remainder, which is 2, over the divisor, which is x minus 1. And so now the original integral becomes the integral of this function. And what's nice about this is the integration here is all very easy. So we can take the integral of x squared very easily. That is 1/3 x cubed. The integral of x is 1/2 x squared. The integral of 2 is 2x plus, now this is the only integral that takes a little bit of work, but if we do this separately, this is a relatively simple substitution problem. We just let u equal x minus 1, du equals dx. You factor the 2 out, and you get the integral of du over u, and that is going to end up giving us 2 times the natural log of the absolute value of x minus 1. Plus c. And this is our antiderivative. So we didn't actually do a partial fraction decomposition here, but the point is that we started with a rather complicated fraction, and after doing long division, the only fraction portion that was left was a very manageable, simple fraction that was fairly easy to find the antiderivative of. So now let's go ahead and talk about the actual process of a partial fraction decomposition. In the first case for partial fraction decompositions, we look at a rational function in which the denominator is a product of distinct linear factors, which just means that all the factors are linear and they're all distinct or different. In this case, we can break it down into a sum of partial fractions where each factor constitutes a denominator and the numerator are all constants. So we can talk about this all day long, but the best way to do this is just to do an example, and you learn this by doing. First thing I want to point out is we do have a proper rational function because the degree of the numerator is 2, the degree of the denominator is 3, so no long division is needed here. The first step is I'm going to take the denominator and I'm going to factor it. And I can first factor it by pulling out an x, which gives us 2x squared plus 3x minus 2. And then we can factor it further by factoring the trinomial here, which is going to be 2x minus 1 times x plus 2. So you might need to review your factoring techniques before doing this section, but this is the final factorization for the denominator here. So the original problem, x squared plus 2x minus 1 over this denominator, can now be written with this new factored denominator. And what I want you to notice here is that this has 3 distinct linear factors. All of these factors have x to the first power, which means they are linear. So when I go to break this down into a partial fraction decomposition, each one of these denominators is going to be made up of each of these factors. And the numerator is just going to be some temporarily unknown constants, which I will just call A, B, and C. So now the whole problem comes down to solving for A, B, and C. And the way to do this is to simply multiply both sides of this equation by the least common denominator. Now when we do this, on the left-hand side, the denominator cancels out, and we simply get what's in the numerator. On the other side, each time you multiply this to a fraction, one of the factors in the denominator is going to cancel. So for example, when I multiply a over x times this, the x is going to cancel out, and we will be left with a multiplied by these two factors here. So we'll have a times 2x minus 1 times x plus 2. Plus, and then when we multiply the second term here, 2x minus 1 is going to cancel out, and we're going to have b times x plus 2. And finally, when we multiply the last term, the x plus 2 is going to cancel out, and we have c times x times 2x minus 1. Now for this case, the easiest way to solve for a, b, and c is to simply plug in values of x that make each one of these factors equal to 0. So for example, if I plug in x equals 0, what's nice about doing that is when I plug 0 in here and when I plug 0 in here, these whole terms here will become 0. And that's going to allow us to solve for a, because these will be gone, and then we'll have a, which will be all by itself, and then we'll be able to solve for it. So let's go ahead and plug in x equals 0 into everything. So when I plug in 0 on the left-hand side, we are just going to get negative 1. When we plug in 0 here, we're going to have a times negative 1 times positive 2. And then again, as I mentioned, when you plug in 0 here and here, you're just going to get 0 for both of those. So what we have here is negative 1 is equal to negative 2 times a, and then if we divide both sides by negative 2, we have a is equal to 1/2. Now to solve for b and c, I'm going to do the same thing, but now I'm just going to plug in a different value of x that is going to make one of the other factors equal to 0. So if you look at your factors here, another convenient value to plug in would be x equals negative 2, because negative 2 plus 2 would be 0. So let's try that. Now, when you plug in -2 to the left-hand side, it's a little bit more work. We'll have -2 squared plus 2 times -2 minus 1. And on the right-hand side, when you plug in -2 here, this whole first term is going to be 0. Plus, when we plug in -2 here, this whole term is going to also be 0. Plus, when we plug in -2 here, we will get c times -2 times 2 times -2 minus 1. So now let's just do the math here. This is +4, this is -4, and this is -1. So on the left-hand side here, we get -1. On the right-hand side, we have -4 minus 1 is -5, multiplied by -2 is 10, and then times c. And so now dividing both sides by 10, we get c is equal to -1/10. So we now know the value for A and the value for C. We just need to find the value for B. To get the value for B, we're going to let x be equal to the number that makes this factor 0. So what number is that? Well, if you set 2x minus 1 equal to 0, you will find out that x needs to be 1/2. So we're going to let x be equal to 1/2. On the left-hand side, when you plug in 1/2, you're going to get 1/2 squared plus 2 times 1/2 minus 1. On the right-hand side, when you plug in 1/2 here, this is going to be 0. When you plug in 1/2 here, this is going to be 0. So we only need to plug in 1/2 to the middle term because that's all that's going to be left. So if we do that, we get b times 1/2 times 1/2 plus 2. Let's do the math now. This is 1/4 plus 1 minus 1. And then on the other side, we have b times 1/2 times 2.5, which is 5/2. And so this becomes 1/4 is equal to 5/4 times b. And now to solve for b, we're just going to multiply both sides by 4 over 5. And when we do that, this cancels out, and we end up getting b is equal to 1/5. So now we're going to take those values, and we're going to come back to our original partial fraction decomposition here, and we're going to plug those numbers in. So we're going to plug in 1/2 for A, 1/5 for B, and -1/10 for C. So let's go ahead and do that. So once we plug those in, our original integral becomes the integral of this. So 1/2 divided by x plus 1/5 divided by 2x minus 1 minus 1/10 divided by x plus 2 dx. Now, if you break this up into 3 integrals, each of these constants can be factored out. And so this becomes 1/2 integral 1 over x dx plus 1/5 integral 1 over 2x minus 1 dx minus 1/10 integral 1 over x plus 2 dx. Now, the first integral here, of course, is just a natural log, but actually these are both natural logs as well. Now, to do these, you're going to do a simple u substitution for each one of these. So I'm not going to show all the details on this. I'll just give you the basic u substitution that you would use, and then try to see if you can work out the details of these to get to the answer. And so that answer is going to be 1/2 natural log of the absolute value of x plus, then we're going to have 1/5 times, and then this integral ends up being 1/2 natural log of the absolute value of 2x minus 1 minus 1/10, and this integral is also going to be the natural log, in this case of x plus 2, plus our arbitrary constant. So this is pretty much our answer here. The only thing I might suggest is that if you have 1/5 times 1/2, we should go ahead and combine those into a single fraction. 1/2 times 1/5 is 1/10. In our next example, we have the integral of dx over x squared minus a squared. All right, so first thing I'm going to do here is write down the rational function, which is 1 over x squared minus a squared. And let's go ahead and factor the denominator, which is fairly simple. It's just x minus a times x plus a. And notice that these are both distinct linear factors. So we can break this down into capital A over x minus a plus capital B over x plus a. And now the next step is I'm just going to solve for a and b by multiplying both sides by the least common denominator, like this. On the left-hand side, we will get 1 because all of this cancels out. On the right-hand side, we'll have a times x plus a. So again, when I say a, I mean capital A times x plus lowercase a. Plus, and then we have b times x minus a. And now to solve for capital A and capital B, I'm going to let x be equal to lowercase a. When I do that, we get 1 equals capital A times lowercase a plus lowercase a. And of course, when you let x equal a here, a minus a is 0. That's the whole reason I did it. So this factor goes away. And so we end up getting 1 is equal to capital A times a plus a is 2a. And I know that's a little bit weird to have a capital A and a lowercase a, but it's actually perfectly fine. So now I'm just going to divide both sides by 2a. And we get capital A is equal to 1 over 2 times lowercase a. And then I'm going to let x equal negative a to solve for b. So if we plug in negative a on the left-hand side, we're going to get 1. On the right-hand side, when you plug in negative a here, negative a plus a is going to be 0, so this cancels out. And we get plus b times negative a minus a. And that gives us 1 equals b times negative 2a. And then I just divide both sides by negative 2a. And we end up getting capital B is equal to negative 1 over 2a. And now that we have those values for a and b, we are going to plug those back into here and here. And when we do that, we get this. And now this integral will turn into the integral of this. So we're going to have the integral of 1 over 2a over x minus a minus 1 over 2a over x plus a. And just like in the previous problem, we can break this down into two integrals. In the first integral, we'll factor out 1 over 2a, and then that leaves us with 1 over x minus a times dx, and then minus 1 over 2a, and then the integral of 1 over x plus a. And these are both natural logs, so we're going to have 1 over 2a times the natural log of the absolute value of x minus a, minus 1 over 2a natural log of the absolute value of x plus a, plus c. And we certainly can leave our answer like this, but we can also combine these. So what I can do here is I can factor out 1 over 2a, and then we have the natural log of x minus a minus the natural log of x plus a, in absolute value, of course. And now using properties of logarithms, we can combine these two natural logs by using division, and we'll have x minus a over x plus a, all in absolute value. And this gives us a slightly more compact answer. But both of these answers here are acceptable. The next type of partial fraction decomposition is when the denominator q of x is a product of linear factors, but some of those factors are repeated. Now, in the case where you have a factor that is repeated, you are going to break it down as such. Now, the best way to explain this is to just go ahead and do an example. So in our example here, the first thing we need to do is take our denominator, x cubed minus x squared minus x plus 1, and we're going to factor that. Now, the way we're going to factor this is by using a technique called grouping. I hope you remember how to group here. But basically, out of the first two terms, I'm going to pull out a common factor of x squared. And out of the second two terms, notice that we don't have anything in common, but we can pull out a negative 1, and that will leave us with x minus 1. And then now you can see that you have a common factor of x minus 1, so we can factor that out, and what is left over is x squared minus 1. Now, of course, x squared minus 1 also factors, and that's going to factor into x minus 1, x plus 1. So the factorization of your denominator is x minus 1 to the second power times x plus 1. So the point is, these are linear factors, but this first factor, x minus 1, is repeated because it's raised to the second power. That just means there was more than one of those factors in the original factorization. Now, something else I want to point out here is that your original rational function is improper, right? The degree of the numerator is greater than the degree of the denominator. So even though this information here is valuable, we're going to have to put that on hold because the first thing we need to do is we need to use long division to simplify this. So let's go ahead and keep in mind that the denominator does factor like this. We'll still need that eventually, but let's go ahead and focus in on the long division. So we're going to take the denominator and divide that into the numerator. And now let's go through the process. X cubed goes into x to the fourth, x times x cubed is x to the fourth. X times negative x squared is negative x cubed. X times negative x is negative x squared. And finally, x times 1 is x. Now we have to change the signs. We're going to subtract, add, subtract. Combining like terms, the x cubed here is going to come down. We're going to have negative 1x squared, positive 3x, and positive 1. And of course, the first terms here canceled out. And now we repeat the process. X cubed goes into x cubed, positive 1 times. Positive 1 times all of these is going to give you all of those. And then we're going to change the signs of all of those. And we end up with, well, x cubes cancel, x squareds cancel. Looks like we just have 4x. That is our remainder. So our original fraction here, we can rewrite this problem as the integral of x plus 1 plus, and then it's just 4x over this denominator. But let's remember that this denominator has a factored form of this here. So let's go ahead and put in that factored form. Dx. Now, we already know how to integrate x. We know how to integrate 1. What we have to do is a partial fraction decomposition on this part. So let's focus in on that. We have 4x over x minus 1 squared times x plus 1. Now, how does this work? Well, when you have a repeated linear factor, x minus 1 to the second power, we're going to start with the first fraction having just x minus 1, and then we're going to increase the power by 1 until we get the power that we have in the original problem. So in this case, it's just going to be x minus 1 and then x minus 1 squared, and now it's equal to the power that we had. Now, had this been a higher power, we would keep going with this pattern until we reach that higher power. Okay, now plus, we also have to have a denominator that has an x plus 1 in it because this is our other factor. And this one's not repeated. And then in the numerator, it's just going to be numbers a, b, and c. And now the whole problem comes down to just solving for a, b, and c. To do this, we're going to multiply both sides of the equation by the least common denominator. On the left-hand side, we'll just get 4x. On the right-hand side, we will have a times x minus 1 times x plus 1 plus b times x plus 1 plus c times x minus 1 squared. So again, I'm just multiplying this to all three of these and canceling the appropriate factors out. Now, one thing we can do is we can just let x equal 1. Doing so will cancel out this term and also this term. When we let x equal 1 here, we get 4 times 1 is 4. And in that middle term, when we let x equal 1, we will get 2 times b. And that tells us that b must be 2. Now I can also let x equal negative 1, because that will cancel out this factor and this factor, or term rather. So these will all be gone. When I plug in negative 1 here, we get negative 4. And when I plug negative 1 in here, negative 1 minus 1 is negative 2, but negative 2 to the second power is positive 4, so we get 4c. And this tells us that c must be negative 1. Now, we still need to solve for a, so to do this, we just have to pick one more value of x. Now, we don't have any other values that will make a factor equal 0, but that's okay. We can just let x equal 0. On the left-hand side, we'll have 0. On the right-hand side, when you plug in x equals 0 here, you get negative 1 times 1, which is negative 1. So that'll just be negative a. Plus, and then we have b times 0 plus 1. Well, b is 2, and 0 plus 1 is 1. So we just get 2 times 1, which is 2. And here, we know c is negative 1. And when we plug in x equals 0, 0 minus 1 is negative 1. Negative 1 to the second power is positive 1, times negative 1 is negative 1. Moving the a over to the left-hand side, we get a is equal to 2 minus 1, which is 1. So now we have a, b, and c. And we can go back to our integral now and break this down into the integral of x plus 1 plus this turns into this decomposition. A is equal to 1, so we'll have 1 over x minus 1. B is 2, so we'll have plus 2 over x minus 1 squared. And c is negative 1, so we have negative 1 over x plus 1 dx. Oops, sorry about the multicolor there. All right, now we just need to integrate each one of these. Now, doing the integration is mostly fairly simple. The integral of x is 1/2 x squared. The integral of 1 is x. The integral of 1 over x minus 1 is the natural log of the absolute value of x minus 1. This is a u substitution. The next integral here is also a u substitution. Let's go ahead and bring this one down and talk about it. So for this one, I'm just going to let u be equal to x minus 1, and du will be dx. And so this will become 2 integral, and we have du over u squared. And this is 2 times the integral of u to the negative 2 du. And that is 2 times u to the negative 1 divided by negative 1, which is the same as negative 2 divided by u, or negative 2 divided by x minus 1. So it's a u substitution problem. Not too bad, but you might want to take it out, and do it separately. And then our last one, this is going to be another simple u substitution that will give us a natural log. And so here we have it. This is the antiderivative. The next case to consider is when your denominator contains an irreducible quadratic factor. So what does it mean to be irreducible and quadratic? Let's talk about this just for a minute. So if I have a quadratic x squared plus 4, this is an irreducible quadratic because if I set it equal to 0 and I solve for x, I'm going to end up getting complex numbers for its solutions, or you might think of these as imaginary numbers. When this happens, we say the quadratic is irreducible. Now you have to be careful because if I have x squared minus 9, we know that this is reducible, right? Because we can factor it. So this is not what we're talking about. But also, even if you have something like x squared minus 5, this is still reducible. Even though you may not like factoring this, it does factor fairly easily. You just have to use a radical instead of a whole number. So when we say a quadratic is irreducible, what we mean is that its solutions, when you set the quadratic equal to 0, are not real numbers. Now in this class, for what we're doing, typically what you're going to see for irreducible quadratics is going to be things like x squared plus 4, or perhaps x squared plus 9, or x squared plus 25. These are all irreducible quadratics, and they're also all very, very common. So let's go ahead and get back to the problem now. So when you have an irreducible quadratic and you're doing a partial fraction decomposition, the way to handle it is to put your irreducible quadratic in the denominator, but now in the numerator you don't just have a constant. You will have a first degree polynomial, a general one, so something like ax plus b. Let's do this example to see what we mean. And by the way, this formula here is going to be very useful once you start integrating irreducible quadratic expressions. So our original polynomial is 2x squared minus x plus 4 over x cubed plus 4x. This can be factored into x times x squared plus 4. Notice that this is proper because the degree of the denominator is larger than the degree of the numerator. This is nice because that means we don't have to do long division. But now when we go to break this down, you do have a linear factor here, x. So that is just going to be a over x plus, and then you have your irreducible quadratic factor there. So that is going to be bx plus c over x squared plus 4. And that's how we break those down. Now from here, the process is very similar. We are going to multiply both sides by the least common denominator. Doing this is going to cancel the denominator here, leaving us with 2x squared minus x plus 4. On the other side, when we multiply this out, the x's cancel out, and we get a times x squared plus 4 plus, now when you multiply these two, the x squared plus 4 cancels out, and you're going to have bx plus c times x. Now the technique for solving for a, b, and c here is a little bit different than the technique we used with linear factors. So first, let's just multiply everything out to see what we have. So we've got a times x squared plus a times 4 plus bx times x is bx squared plus c times x. And then on the right side, I'm going to group the like terms together. So ax squared plus bx squared, we'll put those next to each other. And then we have plus c times x, and then plus 4 times a. So these are our x squared terms, these are our x terms, and this is our constant term. And on the other side, we have 2x squared minus x plus 4. So you can see the same thing. We have our x squared term, our x term, and our constant term. Now, one thing we can do here is we can factor out the x squared. And if we pull out that x squared, we're going to get a plus b times x squared. Now, the reason I'm doing that is because if we have a second degree polynomial on the left side, and that's equal to a second degree polynomial on the right side, the only way this can be true is if the coefficients of the like terms are equal. So for example, the coefficient of x squared here is a plus b. The coefficient of x squared here is 2. So that means that a plus b must be equal to 2. Likewise, the coefficient of x is c. The coefficient of x on the other side is negative 1. So that tells us c must be equal to negative 1. And finally, the constant term here is 4. The constant term on the other side is 4a. So we know 4a must be equal to 4. So if 4a must be equal to 4, that means a must be 1. And up top here, if a is 1, we know that 1 plus 1 is 2, so b must also be 1. And c, we already know, must be negative 1. So just like that, we have the solutions for a, b, and c. Now we can bring that back up here and plug those in to a, b, and c here, and then we should be able to do the integration. So plugging those numbers in, we now need to integrate this function. Now we know how to integrate 1 over x. How do we do this one? Well, the short answer is we just do a quick separation here. So we have 1 over x plus, and now we're going to divide this up into two fractions. So we have x over x squared plus 4 minus 1 over x squared plus 4. Now how to integrate? Of course, we know the first one is the natural log of the absolute value of x. And now how do we do this one here? Well, it's a simple u substitution. We let u equal x squared plus 4. du will be 2x dx. And so when you plug that into a u substitution, you're going to get 1/2 du over u. And so that is going to end up being 1/2 natural log of u. And of course, that is going to end up being 1/2 natural log of the absolute value of x squared plus 4. And then finally, this one here, how do you integrate 1 over x squared plus 4? Well, that is where this formula comes in. So if I have the integral of 1 over x squared plus 4, keep in mind that 4 is the same as 2 squared. So that is like this formula here with a equals 2. And so we know the answer is going to be 1/2 inverse tangent of x over 2 plus c. So now I'll just come down here and I'll fill that in. So we have minus 1/2 inverse tangent of x over 2 plus c. So in the next problem here, notice that we have a rational function with equal degree in numerator and denominator. That means we must do a long division problem first. So we take the denominator and we're going to divide that into the numerator. How many times does 4x squared go into 4x squared? Well, it goes in there 1 time. 1 times 4x squared is 4x squared. And 1 times negative 4x is negative 4x. And 1 times 3 is 3. And then we are going to change all the signs. And that is going to leave us with x minus 1 as a remainder. And so our original integral here is going to become the integral of 1 plus x minus 1 over 4x squared minus 4x plus 3 dx. And so now the question is, well, how do we deal with this? Well, how do we factor it? Can we factor it? Well, I don't know. We can try, right? So 4x squared minus 4x plus 3. If you try factoring it, you will ultimately find that it is not factorable. Okay, no matter what you try here, no matter what combination of numbers you try, it's not going to factor. So why is that? Well, it's because if you take the time to set this quadratic equal to 0, and if you use the quadratic formula to solve this equation, and I beg your pardon for not explaining every single step here, but what you're going to see when you do this, right here, you're going to see that you have the square root of a negative number. And as soon as you do that, oops, in the bottom here should be 8, not 2. Beg your pardon there. But as soon as you have that, you know that the answers here are complex. Now, what does that mean? Well, it means that this is an irreducible quadratic. Okay? And furthermore, we can't really do a partial fraction decomposition because if you look at this, that's all we have. We have an irreducible quadratic and we have a linear function on top. So the only question that remains is how do we integrate this? Well, the answer here is we can take 4x squared minus 4x plus 3. And what I'm going to do here is I'm going to add 1 here and I'm going to subtract 1 here. Now, why am I adding 1 there? Well, it's because if I do that, this will factor into 2x times 2x and negative 1 and negative 1. And if you check that, you'll see that when you multiply that out, you get this. And then we have plus 3 minus 1 is 2. And so that becomes 2x minus 1 squared plus 2. Okay? So I'm going to rewrite this problem now as the integral of 1 plus x minus 1 over 2x minus 1 squared plus 2 dx. And this is a little bit of an oddball problem. So, most problems you wouldn't do this way. This one is kind of special. All right, now from there, what can we do? Well, what I'm going to do is I'm going to let u be equal to 2x minus 1. If I do that, du will be 2 dx. Okay, and keep in mind, I'm only doing that for this part. I don't need to do that for this part of the integral. So when I do that, I can solve for x here. X is going to be u plus 1 divided by 2. And then I can substitute all that stuff back into here. So let's go ahead and make that substitution to see what this integral becomes when we do that. Well, x is u plus 1 over 2. So we get u plus 1 over 2 minus 1. In the bottom, we're just going to have u squared plus 2, right? Because u is 2x minus 1. And then we need a 2 dx here. So I'm going to put a 2 there and a 1/2 on the outside. So that'll give us a 1/2 here, and that'll give us a du here. Now let's work this out. So on the inside there, we're going to have the integral of u over 2, that's 1/2 u, plus 1/2 minus 1 is going to be negative 1/2 over u squared plus 2 du. This 1/2 can be factored out of the integral, and that'll get multiplied to the other 1/2, so we'll have 1/4, and then we have u minus 1 over u squared plus 2 du. Then we can separate this 1/4 integral of u over u squared plus 2 du minus 1/4 integral of du over u squared plus 2. Now, this one we have a formula for, right? So let's just remember that u squared plus 2 is the same as u squared plus radical 2 squared. And of course, I'm talking about this formula. So in our case, a would be radical 2. So this is going to be simple to integrate just by using this formula. Now for this one, we have to do another substitution, which is getting a little bit weird because we already have a substitution. But we're going to let w equal u squared plus 2. dw will be 2u du. We put a 2 here, we put a 1/2 on the outside, and this one is going to become 1/8 integral of dw divided by w. And that's 1/8 the natural log of w, which turns into 1/8 natural log of u squared plus 2. And then what is u squared plus 2? Well, let's remember, u squared plus 2 was this thing, which was the original expression there. So 1/8 natural log, absolute value, 4x squared minus 4x plus 3. Okay, so that's that first integral. And then this integral is just going to be negative 1/4 times, and the formula says 1 over a, so that's going to be 1 over radical 2 inverse tangent of u over a. So it's going to be u over radical 2. So that's negative 1 over 4 radical 2 inverse tangent of u, which is 2x minus 1 over radical 2. So our final answer is this function minus this function plus c. And there it is. And I actually slightly misspoke because remember, we had back here, remember we had a 1 there? The integral of 1 is x. So that also has to be a part of our answer. All right, so here is our answer. So finally, what do we do if our denominator contains irreducible quadratics that are repeated? So for example, here we have an irreducible quadratic x squared plus 1, which is repeated 3 times. And we also have an irreducible quadratic here, but it's not repeated. So in the next example here, they say to write out the form of the partial fraction decomposition. So we're not actually going to solve for it, we're just going to write out how it would break down. So let's go ahead and take a look. First of all, notice that the degree of the numerator is 3, and the degree of the denominator, they don't tell you what it is, but x squared cubed is x to the 6th power, times x squared is x to the 8th power, times x is going to be x to the 10th power. So the denominator is a 10th power, the numerator is a 3rd power, so this is certainly a proper fraction. So when we go to break it down, we're just going to identify we have a linear factor there that is non-repeated, so that's going to be a over x. Then we have a linear factor here that is also non-repeated, so b over x minus 1. Next, we have an irreducible quadratic, which is also not repeated. So that's going to be cx plus d over x squared plus x plus 1. And then this is where it starts getting interesting. Now we have an irreducible quadratic that is repeated to the 3rd power, right? So repeated 3 times. So we're going to have x squared plus 1 in one denominator, x squared plus 1 squared in the next denominator, and x squared plus 1 cubed in the final denominator. And then all the numerators are going to look like this. We're just going to continue with the letters of the alphabet here. So we're going to have ex plus f, gx plus h, and ix plus j. And I know that looks really strange, but again, we're just focusing on how that process of decomposition would work. And of course, you would never actually have to solve for all of these coefficients because that would be a tremendous amount of work. It would take a very long time. But the point is we want to know the process of breaking it down. And that concludes this video lesson.